Hi students, in this video we are going to study what is real depth and what is apparent depth and how it is related to refractive index of the material. Imagine there is a pool. And a coin is kept at the bottom of the pool. But some of you must have experienced, if you are standing near to the pool, okay, it seems that the coin is not here, it is somewhere here. It seems that the coin is being raised. But you will feel that bottom of the pool is somewhere here and the coin is kept here. So some of you may try to grab the coin and you may fall into the water. So this shift in position is what we call apparent depth. So from the surface of the pool, this much is the apparent depth. And the actual depth of the pool is what we call the real depth. So real depth means the actual distance of the object beneath the surface, whereas apparent depth means it is the depth of an object in a denser medium as it is viewed from a rarer medium. The depth of an object which is placed in a denser medium when viewed from a rarer medium, and this happens due to refraction of light. So in this video we are going to see how this real depth, apparent depth and refractive index of the medium are related. So imagine this is a rarer medium, this is a denser medium, this is air, this is water, okay, and an object is placed at the bottom of the water. Okay. Now two rays from the object is reaching our eyes. One ray is traveling straight, hitting the surface normally. I told you if the ray is traveling and hitting the surface perpendicular normally, the ray will remain undeviated after refraction. Or there won't be any refraction, the ray will be undeviated. So the ray will directly reach the person's eye. And for a ray from the object which is incident on the surface obliquely, that means at an angle, it gets refracted. So this is the angle of incidence, this is the angle of refraction. Okay, now we are going to apply Snell's law and find out what is the relation between real depth, apparent depth and refractive index of the medium. So applying Snell's law, and write sin I by sin R is equal to, in this case we are taking the light rays traveling from the denser medium to the rarer medium. So this is medium 1 and this is medium 2. So you can write N 2 1, or if you want you can write N A W. You can name it as you wish. Okay. Now we are going to find out what is sin I and what is angle I and angle R. For that we are going to use two triangles. Triangle A, we call this as point O, A, O, B. From that we will find out what is sin I, and from triangle A, I, B, we will find out what is sin R. So from triangle A, O, B, sin I is equal to, you know what is sin theta? Sin theta is opposite side by hypotenuse. So it is AB divided by BO. Similarly, from triangle AIB, sin R is equal to opposite side by hypotenuse BI. Now, on applying the value of sin I and sin R in equation 1, we will take this as equation 1, we get N21 is equal to sin I, that is AB by BO divided by AB by BI is equal to BI by B O. Now you all know how we are able to see an object, isn't it? Light rays from the object reaches our eye, and through the pupil the light rays enters, reaches the lens, and on the retina part, reaches the retina part, and we are able to see the objects. So in this case we will be able to see ray B only if it is very close to ray A, means point A. Otherwise the rays from the point B won't enter our eye if it is very far away from point A. So the ray BC will enter the pupil of our eye only if point B is very close to point A, which means instead of BI we can write AI, and instead of BO we can write AO. So we can write refractive index N21 is equal to AI divided by AO. Now, if you look into this diagram, you can see AI means it is the apparent depth and AO is the real depth, isn't it? So, you can write N21, that is refractive index of air with respect to water, is equal to apparent depth divided by real depth. But usually when we say refractive index, we say refractive index of for second medium, that is water or glass with respect to air. That's our standard notation of writing refractive index. So instead of NAW we have to write NWA. So what do you do? We take the inverse on both sides. So taking the inverse on both sides, we can write NWA, which is equal to 1 by NAW. Is equal to, generally we are going to write first medium is air, we can write it as N itself, and is equal to real depth divided by apparent depth, or apparent depth is equal to real depth divided by refractive index of the material N. Usually air is having refractive index 1. All other materials will be having refractive index greater than 1. So definitely from this equation we can say apparent depth is always less than real depth. Why? Because since refractive index value will be greater than 1, you can say real depth is always less than, apparent depth is always less than real depth. Next, we are going to find out normal shift. Normal shift means it is a difference in real depth, height difference in real depth and apparent depth. It is defined as the height through which the object is raised in a denser medium when viewed from a rarer medium. Okay, and it is denoted by the letter T. Or so D, normal shift D is equal to real depth minus apparent depth, is equal to real depth minus relation between real depth, apparent depth and refractive index is apparent depth is equal to real depth divided by refractive index. So we can write this as minus real depth divided by the refractive index. So taking real depth upside, we can write is equal to real depth into 1 minus 1 by mu. So normal shift D is equal to real depth into 1 minus 1 by mu. Okay. Now, next we are going to study about apparent shift in position of sun. You must have heard in your lower class that the sun which we see during the sunrise is not actually the original sun. The one which we see after sunset is not the original sun, it is an apparent sun. Now, why this phenomena? It is because of the atmospheric refraction, which means before the sunrise itself we are able to see the sun, and after the sunset also we are seeing the sun. So there is a difference of time, and this is because of the atmospheric refraction. Now we all know Earth's atmosphere is made up of different layers, troposphere, stratosphere, etc., 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 etc. So with altitude or with height, we can say as we are going up, the density of the atmosphere decreases, which means from the surface of the earth with altitude, the density decreases, which means light will be traveling from a denser medium to a rarer medium. Now think the opposite. Imagine, sunrise means sun will be above the horizon, isn't it? Now, before sunrise, sun is in this particular position, and the rays from the sun will reach the atmosphere. What happens? The rays traveling from a rarer medium to a comparatively denser medium, because as we are going down, the density of the air is increasing, or density of the atmosphere is increasing. So, after touching the Earth's outer atmospheric layer, as the light is getting refracted, it is traveling from a comparatively less denser medium to comparatively more denser medium, or we can say from a rarer medium to a denser medium. Now, what happens when light travels from a rarer medium to a denser medium? Definitely it will bend towards the normal. So, when the light ray touches each layer of the atmosphere, we can find out there is a bending of light towards the normal, like this. So, once the light ray reaches this point, it will get bended, again it will be getting bending, again it will get bent towards the normal. And for a person who is standing here on the surface of the earth, we know for us light travels in a straight line. So, for a person who is standing on the surface of the earth and viewing the sun, it will seem that the sun is somewhat here. So, this will be the sun. But actually, where is our sun? Sun is below the horizon. But due to the repeated atmospheric refraction, what happens for a person who is viewing the sun appears to be at this particular position. So, this is actually the real sun, and this is the apparent sun, or apparent shift in the position of the sun. And this deviation is about 0.5 degree, or we can say we are seeing the sun 2 minutes early before the actual sunrise. Same way, when sun sets, what happens? Same phenomena happens And after sun setting or after sun going to the below the horizon also, we will be viewing the sun for 2 minutes. So our day is 4 minutes longer than the original time. I hope you got an idea. Due to the repeated atmospheric refraction, that means when light travels from a rarer medium to comparatively denser medium, it bends towards the normal, and for a person who is standing here and viewing the sunrise, sun appears to come from this position, appears to be in this particular position. And this shift or this apparent position of the sun results in such a way that for us, sun appears to be there 2 minutes before the actual sunrise, and same way during the evening time when the sun sets, sun will be there for 2 minutes. So there is a delay in sunset because of the atmospheric refraction. Thank you.